thank you for everybody for inviting me. Perfect, I'm ready. So actually my talk will be essentially on the basis of my ERC grant, so you will know a little bit what this is about. And I want to introduce this notion of queryable self-deliberating dynamic systems. And to do so, I would like to start with an example. And the example is the following. After a long weekend, a human supervisor inspects a manufacturing system and notices that the production line has slowed down significantly, though it's still producing. She queries the system on what the system is doing. And the system reveals to her the revised process, the revised manufacturing process, which is now avoiding the production Ireland 176176, so it's not going to that particular robot, by repurposing the tools in the Ireland 176671 and sending out the items there. Then she queries why the system has reprogrammed itself to do so. And the system answers by showing that at a certain time on Sunday, the Ireland 176176 started to produce too many errors, too many defective items. So instead of shutting down the production line, very important, it can reprogram itself, so it can deliberate on its own, autonomously, on what to do. And the other important thing is that we can say explainable. Nowadays we say explainable. Okay? Here I'm actually saying queryable, which is a little bit different in the sense that when you say explainable, there are two parts of it. One part is being able to query, to ask what is happening. The other part is presenting the answer. Okay, so I'm not concerned with presenting the answer. Okay, the presentation part, which is also very important, there is a lot of work on that. I don't care in this talk. I care about the essence. So can we get the information out of this system? Okay, so this is querying. Obviously, query is very important because we are giving to this kind of system the ability of reprogram themselves. Okay? And so we want to have some human supervision, human guidance, okay, human understanding on what these machines are doing. And this is a very well known problem nowadays. No? It's the reason why explainable AI is so much involved. If we give autonomy to a system, we want to have some way of supervising it. So this is what queryable self-deliberating dynamic systems are about. And now I want to talk a little bit about how we can build this kind of system. Okay, so first of all, what is a dynamic system in general? Okay, a dynamic system in general, we can think in a very abstract term. Sorry, this microphone. Okay, we can think in a very abstract term as a system that is interacting with an environment. Essentially, is a function. It reads the environment, the input. It can, let's assume, it reads the entire history. Okay, it reads and considers the entire history. I don't want to limit in any way this system, and produce outputs. Outputs that are given to the environment does something, produce new input, and so on and so forth. Okay. Now, this kind of system is completely general. This is the most general kind of system we know in computer science. All our programs are of this form. However, in most computer science, this system is predefined in the sense that the function is given once and for all. Instead, also in AI we have this system. Obviously, yes, we have an agent, now we call the system agent, okay, and the agent is acting in a world. It's observing the world, acting in the world. So now we have a sequence of observation, all the history so far, and now we have to decide the next action to do. And so it's very much the same kind of system. But there is a difference. And the difference is that the function is not predefined. We don't assume that this function is predefined because somehow we think that the agent thinks and then acts. Thinks means synthesize the function, and acts means follows the function. Now, this kind of system is ubiquitous in AI. Okay? We can see it in very many areas. But what is important, and I want to underline somehow, is that this system has a first-person perspective on self-deliberation. So who's deliberating? Not the designer. It's not that you are helping the designer to synthesize the new program. It's the system itself that is deliberating its own action. Okay, so it's a first-person kind of deliberation. And we can find these kind of things in knowledge representation. Reasoning about action is all about that. In planning, obviously, planning is about that. But also in MVP, sequential decision processing, reinforcement learning. And in particular, if we consider planning or reasoning about action, what we have a very similar picture. We have the agent, we have the world. The world, the agent extract from the world fluence. So this is essentially the model that the agent is using in order to understand the world. So it now gets a sequence of fluence evaluations. So this is a proposition, a formula somehow we can think of them, of what the word statement about what the word is. And then it does its action. The action are actuated, and then new fluent configuration are produced, and so on and so forth. So this kind of system are clearly, so they are described somehow high level. So they clearly have a precise model of the world and a goal. And this model of the world and this goal can be actually analyzed because it's explicit somehow. It's in the fluence, right? It's in the fluence. It's expressed through the fluence. So it is both self-deliberating and essentially by definition queryable. But if we consider instead reinforcement learning, we have a very, very similar picture. So now we are extracting from the world features. And we are using the features to generate our action, okay? The sequence of features to generate our action. And then we do the action in the world, get new feature, and so on and so forth. Now we don't have an explicit goal. The goal is given through rewards. The goal is given through rewards. And we have from the world some sort of reward extraction. Now, the interesting thing about reinforcement learning is when the feature itself are learned. So you don't have them predefined. Okay. Now, if, for example, all deep reinforcement learning is all based on learning also the features. The point is that when you learn the features, this feature will not be in your language. They will be in the language of the machine. So what it means that it is a self-deliberating system, but somehow it is not queryable. And maybe it's also right that it's not queryable. You don't want to query everything. For example, if you query yourself about how do I ride a bike, how do I ride my bike, I tell you, you don't know how you are able to ride your bike. Why? You don't have the language to talk about it. Okay, so it's fine. So there are certain things don't need to be explained. That's fine. Obviously, this is, however, a problem if you want to supervise somehow your system. Okay, so let me talk a little bit about reasonable action and planning. I think these are somehow the starting point for this kind of system I'm talking about, because they are based on a model of the world, and since you have models, essentially you have human comprehensibility. These are also high-level models somehow, so you can read them, you can model check them, you can verify them. And also, if we consider planning, we have also fantastic algorithm for solving planning in several variants. Okay, so we have fantastic algorithm for classical planning, reachability. We have fantastic algorithm, maybe not as fantastic, but very good algorithm for adversarial reachability, which is non-deterministic planning, and also variant with fairness, etc. And these algorithms are also essentially can also be used for solving safety problems. Before we were mentioning service composition. Service composition is all about some sort of planning, but planning not for reachability, but for maintaining the possibility of simulating. This maintenance is a sort of safety condition. And essentially, the algorithm is really much the same. However, there are very important limitations in current KR and in current planning. The first thing is the goal. So we are specifying the goal like a state of affair. But if you want to specify a task, how do people specify task in formal methods as a state of affair? No, they specify with formal specification language, maybe based on temporal logic. So these are very rich language for specifying the goal that actually are able to describe the sequencing, the allowed sequencing of activities. And since we are talking about process, this is what we want to do. We also want to have this ability of talking about tasks in a very general way. Also models, I will not have much time to talk about this, but also model, we are essentially stuck with a sort of Markovian model of the world in a certain state. We do an action, we move. Modeling, we are essentially stuck with a Markovian model of the world. We are in a certain state, we do an action, we get to a new state. But actually, we think these functions are not about the current state. They should talk about the entire history. Why are they talking only about the current state? You can say, okay, but I'm going to remember the entire history in the current state. Well, be careful. Be careful when you do that. You are paying for storing the history in your current state, and maybe you are paying more than what is needed. So we don't want to be Markovian necessarily. And the other thing is that we want to retain sound and complete algorithms. Possibly we would like to have a computational assessment of the complexity. Obviously we know the complexity, actually I'm going to show you in a minute, the complexity somehow is very weak, a very weak notion, okay? But give us some sort of orientation on the kind of difficulties we found. Now, the point is that for addressing this part of things, three initial points, what we really need to do, or what I think it's a good way of approaching it, is to look at formal methods. So this is what I'm going to do next. Before saying that, let me tell you that also we are interested, obviously, in integrating model-based and model-free approaches. So we would like to have both the reinforcement learning and the knowledge representation together somehow, so that you can still use deep reinforcement learning, but you can also understand what is going on. And the other thing is that most of this work is actually based on positional logic. Okay? Instead, we are interested in relational logic and relational formalization. Why? Because we are talking about a real system. A real system is typically written in UML with BPM describing the processes. We want to have that kind of... Okay, so formal method. This is the first thing I want to talk about. Formal method. In particular, I want to talk about synthesis. So synthesis formal methods, obviously, is very, very important. It's a dream. Okay, the dream is the following basic idea. Mechanical translation of human understandable task specification, okay, to a program that is known to meet the specification. So you have a proof that is okay. Very interesting and general statement. And actually, this thing has been studied a lot since the 60s And it has been studied in two variants. One is the classical variant. So somehow we are interested in synthesizing a function. You give me the input, you give me the output that you want, synthesize the function to produce the right output. Okay? But I'm interested here instead in the reactive version of it. So this came much later. So it came around the end of the 70s. So we were interested very much in computer science, in concurrency, and the fact that the system was continuously interacting with other systems, the environment, and then now you want to describe, we want to synthesize a process that can act in the correct way with the environment. And by now, we have a fantastic theory of reactive synthesis. It's elegant, comprehensive theory. And it is very deeply connected with planning in fully observable, non-deterministic domain, so-called fond planning. And I'm going to show you with this slide that they are almost the same thing. So, this is planning in non-deterministic domain. What it means you do an action, but the environment can answer with several possible effects. Okay? So you have essentially two players. One is the agent that does the action. The other is the environment that answers with the effect. The effects are fluence evaluation. The actions are what we call action. And also we have a domain specification. We have a domain specification. This is very interesting. We have a domain specification that somehow it's our model of how the environment works when we do our action, or how the environment answers. It's a model we have that we can use when we do planning. And then we have the goal. The goal is reach a certain state of affairs. In reactive synthesis, we also have two players. Okay? One is the player that plays the inputs, X, and the other player is the system who plays the output. So you have environment and a system, which is the agent. We don't have a domain. It's not considered a domain, but the goal is completely general. It's any kind of logical formula. And I'm talking here about linear time logic, so logic that talk about the sequencing of activity. This is very important. Sequencing of activity. For example, linear time logic is possibly the logic of election in this field. And now when we go to the synthesis in both cases, it's a game between two players. And what you want to do, you want to synthesize a strategy to win this game. Okay? You have an arena, and the arena, in the case of planning, is the domain. In the case of synthesis, it's any value to X and Y. There's essentially no arena. A very general arena. We have to play the game, and we have the strategy that is essentially the same for both of them. You want to synthesize anything from the history so far, the next move to do for the agent. Now, the algorithm for planning, let's go to the algorithm. The algorithm for planning are pretty good. Okay, this problem is X time complete. But actually, there are very good algorithms. Algorithm for reactive synthesis, how difficult is that? It's known since '89, this double X time. However, the problem is that from '89, we are looking at good algorithms that actually perform well in practice. And we have not found them yet. So, take example. Or, what is the algorithm for synthesis? Okay? Let me give you an algorithm for synthesis so that we understand a little bit the flavor. You don't have to understand the algorithm in detail. So the algorithm works like, you take the linear time formula. Okay? This is essentially a formula that will be true in certain runs. What are runs? These are traces. What are traces? Infinite sequences of inputs, okay, and inputs and output actually, propositions, and you transform this formula into an automata. Okay, this is an automata on infinite object, an automata that recognizes infinite strings, and this is called a Bookino deterministic automata. The steppiece exponential is not actually, this part of the algorithm is pretty good, actually. The automata is not necessarily much bigger than the formula. A little bit, I mean, it's bigger, but it's not that bad. However, you need to determinize it. Okay, you need to determinize this automata. And to determinize it, unfortunately, Booki automata have a very bad features. You cannot determinize a Booki automata. If you determinize it, you lose expressive power. It's not like normal automata. So you need to go to a fancier form of automata. These are called parity automata. Okay? The cost of this determination is also exponential. But the problem is that we don't have good algorithm for it. Essentially, we don't know how to do this fast in practice. So we know that this is exponential in worst case, but unfortunately, it's very bad even in the normal standard case. And 30 years of work, we have not solved the problem. And now I want to report a little conversation that I had with Moshe Vardi in 2012. Okay? So I said, we were looking at the synthesis, and I said, we should consider synthesis on finite traces. I'll tell you in a moment why. They are important in AI and other fields. And Moshe answered, oh, but that's easy. And I replied, precisely. We want it easy. Keep it simple. So why finite traces are important? Finite traces are being used a lot. A lot of time in AI when we talk about linear time logic, linear temporal extended goal, etc., we are actually focusing on finite traces. Why? Because we think that the agent will perform a certain task for a while, but after a while, it will perform another task. You don't want to stack it in a single task for all its life, right? So it's very natural to consider finite traces in that case. And also finite traces have been considered a lot in business process management, where we assume that the business process, the process, will eventually end. Sure, you don't want to get, I mean, this field is not studying servers, it's studying procedure that start and end. Okay, so consider finite traces, we consider linear time logic on finite traces. And what is linear time logic on finite traces? It's linear time logic, standard linear time logic, except that it's interpreted. So for example, when you have always means at every point in time. In infinite traces means forever. Here it doesn't mean forever. It means at every point in time until the trace exists. When the trace ends, you don't care anymore. Eventually means there is a moment in time along the trace before the end of the trace where a certain thing is true. And then until A is true, until B becomes true, and so on and so forth. And actually this has been studying. We know that this corresponds to first order logic on finite traces. And then there is a variant of it that corresponding to monadic second order logic on finite traces, which is essentially the most powerful language we have on finite traces, decidable language on finite traces. And in order to get that, what you need to do, essentially, you need to stick a regular expression in the eventuality. So you need to say, not that eventually a certain thing is true along the trace, but eventually there is an execution of a regular expression that now you can think as a program, like in dynamic logic, that makes that such that at the end a certain formula is true. And actually this parallelism between regular expression and programs has been actually one of the bases of Golog and Congolog in situation calculus, and indeed you can express if then else and while as regular. You know, there are many examples, I don't really want to go into them. Now what is interesting is this thing over here that says that in a formula is true in a trace if a certain automaton, now it's a deterministic finite state automaton, recognize the trace. over here. So if T belongs to the language of a certain automaton, and this automaton now it's a DFA, so the one that we study at school. It's not a fancy automaton infinite traces, it's the standard deterministic automata that we all know about. And actually, it's actually pretty easy to, from formulas, from simple formula, to get the corresponding automata. Here, I have some examples. And now we can go to synthesis. And synthesis for finite traces is essentially the same algorithm as before. He says, take the formula, compute the non-deterministic automata, determinize it, play the game. Okay? Now, when you determinize the automaton, what you use subset construction. The one that we study at school. But the one that you study at school, it's actually a fantastic algorithm. It can be implemented symbolically, it allows for heuristic, you don't have to do it explicitly, you can do it on the fly. So, result, exact same complexity. But now, we have scalable algorithm. And there are papers now that are coming out in days that show order of magnitude advantage of using kind of algorithms instead of, for example, translating everything to linear time logic and do synthesis in linear time logic. What about the domain? This is synthesis. Remember, in synthesis, we don't have a model of the world. We don't have a description of the domain. Why we don't have a description of the domain? If we think about it, this is very strange. How come that we don't have a description of the world? Well, because in fact, you don't really need it. Okay? So if you have a description of a domain, you can do the synthesis. You can do the synthesis by synthesizing an implication. So formulas describing the domain implies formulas describing it. However, this is not very good because we're going to be double exponential in this huge formula. And notice that there is a big difference between the formula describing the domain, which is a model of the entire world, so it's going to be very big, and the formula describing the goal, which is the model of a little task. Okay, that says, I want to do first this task, first this action, and then that action. Okay, so can we do better? Yes, we can do better. And actually, in planning, we have always done better because we have kept the domain separate from the goal. So we say the domain is the model of the world. We don't want to treat it as we treat the goal. And indeed, because of this very different nature, we can keep things separate and take advantage of keeping things separate. I'm going to skip this. Keeping things separate, what do you mean? Now I have an algorithm that works. Give me the formula. You give me also the model of the domain. Now it turns out that the model of the domain, it works like this, no? Given the current state, given the action, I provide you an effect. This is the word, right? But what it means, if you give me a state, you give me the action, and you give me the effect, I'm going to have only one next action. So actually, the non-deterministic domains are in fact deterministic automata. They can be expressed as deterministic automata. So now we have something very nice here. We take the formula and we transform it into a DFA, essentially. And what about the domain? The domain, I keep it out of this translation. And I translate it directly into the domain in polynomial time. And now I do the computation for winning the strategy. And indeed, I have an exponential improvement in the domain just because I analyze things better. And now I understand that I don't need to do all this manipulation of the domain, and the problem remains Einstein complete in the domain, in double Einstein complete. Keeping goal and model separated, as we do in databases when we do schema complexity and data complexity. Okay, so this linear time logic has been very, very fruitful lately, and there is a lot of work done by my group, by a group in Toronto, by groups in China, by the Moshe's group, and actually something interesting to look but I want to move on. And I now want to consider the possibility of having multiple models at this. In particular, I'm very interested in having, on the one hand, model for reinforcement learning, and on the other hand, model for knowledge representation. So this is the kind of architecture I'm interested in. So I have a system, the learning agent. Now the system is the learning agent. We call it the learning agent, like in reinforcement learning. We have an environment, and if you follow the blue line, you get, so if you follow the red line, you get the standard setting for reinforcement learning. You extract features are provided to the agent, also rewards are provided to the agent provides action are sent to the ward, and so on and so forth. However, on top of that, I also extract fluence. Now notice, I'm extracting fluence from the world, not from the features. What it means? It means that the features and the fluence will be unrelated. They will be related only through the world. Okay, so I'm extracting the features, the fluence, sorry, and I'm sending them to a KR-based monitor. Okay, so this is a model of the world, something that I want to do, maybe a model of a task, whatever. And what I do, I let this monitor send rewards to the learning agent. So now the learning agent is getting rewards, on the one hand, from the world, so it learns to walk. Okay, but on the other hand, from the knowledge representation, it learns to get out of the room quietly. Okay? Now this notion, very interestingly, is related to Star Wars. In Star Wars, they invented this thing. It's called the restraining bolt. What is a restraining bolt? It's written here. This is from the official Star Wars site. Restraining bolt is a small cylindrical device that restricts the droid action when connected to its system. Droid owner installed the restraining bolt and to limit the action to a set of desired behavior. Look at that. So we are controlling somehow, okay, with safety measure of some form, the droid through this restraining bolt. Now, this restraining bolt is actually an amazing concept because, first of all, in Star Wars, who uses the restraining bolt? Essentially, the Java guy. These are pirates. Okay, they steal the robots and they put this restraining bolt so that they cannot escape. Okay? And the interesting thing is that they use the same restraining bolt for many kinds of robots. Okay? For example, our two heroes both have the restraining bolt. What it means that the restraining bolt cannot really interface to the system of the robot, because obviously the system of the robot will be done by some manufacturer, and if there are two manufacturers, the internals of the robot will be very different. And somehow, must work anyway. So, the question is this really science fiction? Is this just a crazy idea? And actually, the answer is no. We can actually build this very board, although it looks very strange. So, again, the point is that we have two distinct representations of the world. One for the agent and one for the restraining. Restraining bolt, assume it's an authority. Maybe the European Union tells you your robot can be used only if you plug in this restraining bolt. Okay? And the two representations are unrelated because the European Union doesn't know who's going to manufacture the robot. So they are unrelated. So, is there a relation? Yes. They both talk about the world. So there is a relation. They are all both talking about the physical world. So this is somehow the glue. And indeed, you can build some sort of restraining bolt in this way. For example, you can specify here the task using linear time temporal logic. And every time the sequence performed by the agent satisfies a certain formula, it gets a positive reward, a very high positive reward. And then The agent obviously is a learning agent. He learns various things, how to move in its world, etc. But also has these additional special rewards coming. The formula. Okay, notice that the formula, you can understand the formula. You write the formula high level. You write the formula. Human understand the formula. You don't understand the features. Sorry, these are learned. And let me give you some examples. Okay, I don't have here the movies, but you could have the movies that shows how this thing works. So let me look at a very simple AI gene problem, the breakout. So the breakout is you have a paddle, and you want to break these bricks. Okay? The point is, let's go into the representation. What is the representation? Well, the paddle, the agent is controlling the paddle, and what he really sees of all this world is only the position and the velocity, vectorial velocity acceleration of the paddle and of the ball, nothing else. In particular, he does not see the bricks. Okay? So it's like playing tennis, okay? But you're playing tennis in a so long field that you don't see your adversary. Okay? There is fog. You don't see your adversary. But you understand from, hey, this is good, this is not good, rewards. You understand somehow how things are working. Now, I want to express that you want to remove these bricks. You want to remove these bricks in turn. So you want first to break the first column, then the second column, then the third column, etc., etc. Observe that this thing cannot even be expressed in the language of the agent. The agent does not have the bricks. Okay? But the restraining bolt can have this, can use this language. And indeed, if you make it run, the system learns actually to break the bricks one at the column one at a. And here I have another example coming from the RoboCup. And now we have a robot is going around, is giving drinks to people, okay? And he knows his position, knows how to reach people. People are seated in stalls. And what we want to have a restraining bolt that says, don't serve alcohol to minor. Notice that the robot doesn't know what it means minor. It doesn't even know the identity of the people, okay? But the restraining bolt can maybe learn the identity from some face recognition and understand the minor, if somebody is minor or not. And again, you can prove that, I mean, you can, it can be shown that this thing actually works. This robot learn not to serve alcohol. How this thing works? Well, what is important, I don't really know. What is important is that, we tried actually for a certain example, then we tried for a second example, then we tried for a third example. At the beginning, we were thinking it's a sort of approach. This works in some cases. But then it was working in the first example, the second example, the third example, the fourth example, and then maybe this works. And indeed, we prove a theorem. There is a theorem that tells you this thing works always. Okay? So at the limit, obviously, works always at the limit. Theorem in the reinforcement learning sense means at the limit. Okay, so now the connection between my KR monitor and my learning agent in the case was very, very loose. You can always think, and there are a lot of papers thinking about a stronger connection between the two, and in fact, this is a very active research area, and there are many people working with these things, mostly people from formal medicine. Okay, I'm almost closing, but I want to talk a little bit about lifting to first order. So, remember my original motivation. I was talking about a manufacturing. I was talking about a business process. I was talking about the Internet of Things. I was talking about something real, okay, not propositional. Now, a process, I mean, a dynamic system in reality is formed by data and you need to consider the two. And how you represent data? Well, software engineers already tell us how we represent. We can represent data, maybe we UML class diagram, and we represent process, maybe with BPM class diagram. So these are very well-developed tools to write big data object repositories and processes. And actually there is some work that shows that you can connect these two and actually get a system that has both aspects. Also, although traditionally they're considered separate. Now, again, let's look at this from a formal point of view. Well, if you have data, essentially data is a database. It's a database. You do action, you change the database. But what it means? It means I'm starting from an initial database. I can do action. I can do very many actions. I can add a certain person. I can add another person. I can register to a certain conference and then submit a paper to a CAI. Many things. Things change over time. How many states we need to consider? Infinitely many. These are essentially all the possible state of the data. So this kind of transition systems, so this kind of evolution described typically as transition system, are transition systems that are infinite. And unfortunately, model checking is all about checking transition system, but it works for finite transition system, not for infinite transition system. When you have an infinite transition system, it becomes further transition. However, there is a very interesting result we discovered in reasoning about action lately. Okay? And the result is the following. If your state is, we say, bounded, then you can take your infinite transition system and transform it into a finite one that is bisimilar to the infinite. And so you can model check the finite one instead of the infinite. Now, what it means bounded? It's a technical definition. Essentially means that you are not talking of more than a certain amount of object in any state. Of the other, you don't say anything. This is the meaning. And one way to understand it is to think of a bookshelf. Think that your memory, the memory of the system, it's a bookshelf. Okay? You can put whatever books you like. Okay? When you're young, you put Asimov. Okay? Now you're older, you want to read ancient Greek classics. By the way, this is not me, somebody else, but okay. But the problem is that your bookshelf is the same. So in order to read these books, you have to throw away the Asimov books, get the ancient classics. So what it means, I can read how many books I like in my life, but at the same time, I can only consider simultaneously a finite number of them. Okay, actually a fixed number of them, 10, okay, 1,000, 1 million, okay? When you are in this situation, this algorithm, this theorem applies, and you get essentially decidability for entire Mukaku over this transition system. Conclusion. So, we are starting to build this kind of self-deliberating system. For example, in business process, it is now very in vogue to say, you don't want to write the program for all the possible exceptions, because there are too many. So we need to find a way of generating automatically the response to exceptional circumstances, okay? This is self-deliberating dynamic system. And when you do this, it's very important that you make them queryable, because you want to have system automatic, but under the humans. There are very important advancements. So sometimes we say the knowledge representation is good old AI. Okay? I think that this is very, very wrong. It's actually good old AI. It's old. It's not good because it's old. Okay? Instead, we need to go beyond this kind of AI. And what we need to do in KR, we need to connect to formal methods. We need to connect to databases. We need to connect to business process modeling. So there are other fields that are model-based. I think the KR means model-based. It's the essence of model-based AI. There are other places in the world in computer science where they are studying model-based computer science. There are a lot of important advancements there. They need to be incorporated in knowledge representation. Notice that normally in these other fields, you have a third-person view, not a first-person view. What it means, it's for the designer. These are tools for the designer. Instead, what you want to do, you want to put this tool in the mind of the robot. This is the difference between KR and formal methods, okay? So you want to put this thing in the head of the robot and not in the head of the designer as a tool for the design. Several issues remain open, obviously, but also somehow there are important advancements that are coming out lately, and for example, this LTL on the finite traces, Moshe Vardi is now completely in love with them, more than me, okay? It's really important because it gives you real algorithm that works in practice. And so you can do synthesis, but also not theory, but practice, which is very important. Merging model-free and model-based dynamic system, what is going to happen in the next year. Okay? And the witness of this is the recent proposal for European Network of Excellence that we submitted last week, which is all about mixing model-free and model-based. Okay? And lastly, I want to say a word on something that we didn't mention at all. So we have this robot that is self-deliberating. So you give a task, you will understand how to do it. Okay? But wait a moment, who's giving the task? Who's giving the task? Essentially, for now, we are treating the system as obedient soldiers. We give the task, you obey and do it. Okay? There is some work recently saying, no, obedient soldier is not good because you can tell a robot, kill my friend because I don't like him anymore, and he should say something, he should say no, okay? Build ethics, okay? Now what you want somehow still an obedient soldier, but with ethics, okay? That actually somehow, sometimes they say it's rebellious, they call it a rebellious agent, okay, because they don't obey to order. But actually, these are only two modalities. So the disobedient and the obedient soldier. These are only two modalities. But I can have incredibly many modalities here. So for example, there are cases in which I say, I want to go to the cinema. Francesco, what do you want to do? I want to go to the theater, okay? And then we stay home watching TV, okay? This cannot, I mean, all of you have experienced this, right? This is another modality, okay? It's not there. So I think it's important to start studying also how to generate goals, okay? So the goal formation, it's essentially wild field, very few papers, actually becoming important. Because once you self-deliberate what to do, maybe you want to also deliberate the task for which you are doing what you're doing. And I'm done. Thank you.
Thank you. Is there any question?
Okay, so what is the first question? Okay, yes. So first of all, this is a very, very general system and a very, very general result. It tells you that you can always do it. What it means, be careful. So what about if the learning agent is a pig and what I am rewarding it is if he flies, okay? It fits this scenario. He learns at best. So it optimizes to get the most of the rewards, but it is not guaranteed that it gets exactly the constraints. So this is a very soft kind of constraint. If you want to have harder constraints, obviously you can, but now you need to connect a little bit better to the agent, okay? You need to connect not so loose, you need to know essentially you need to look at the features, and you need to understand the mapping between the features and the fluence required for your specification. And there is a lot of work. Respect to the two rewards, obviously, yes, this is a very important problem in reinforcement learning. If you are getting rewards from several sources, how you balance them. Okay, how you balance them. A lot of work on this. Actually, not yet work on this kind of restraining bolt, etc., because this is very new. This is 2019 work, right? So not yet. Here, essentially, we were thinking about scaling factors, okay? But also scaling factors, also that needs to be considered. So, yes, people in machine learning are interested in understanding the relationship between the various reward sources. And extracting the feature, extracting the fluence, extracting the features, how you do it. Yes, maybe you do it through machine learning, okay? Maybe you write a function from very low-level features to, sometimes they call it, I don't know if you ever heard this thing, semantic annotation in robotics, semantic annotation. What do you mean semantic annotation? Certain pieces, I don't know, of a map, they say this is kitchen, okay? Okay, kitchen is the feature, the fluent extraction. Okay, that's the fluent extraction. It's a field of research. Okay?
Another short question. I have just a comment. I think that there is some interesting room for using notions from game theory, for instance, both in the KR-based monitor and on the goal part. Because this idea of controlling from the...
Absolutely. So let me tell you, I'm talking about a very classical problem of synthesis, reactive synthesis, okay? But nowadays there are a lot of variants of synthesis that have been studied, especially in multi-agent systems. Yeah. Okay? In multi-agent systems, this is a two-agent system. In a multi-agent system, you may want to do things differently, and there are strategy logic that talks about, I have a strategy such that you have a strategy, and then Nash equilibria and connection with game theory.
Also
yes.
For the regulation part. So
yes. Yes. Absolutely.
Systems, you have
absolutely.
Some regulation
I agree.
Which fits very good in this.
I totally agree.
So let's thank again Giuseppe. We are a bit late, so I suggest to shorten the period for the coffee break, and we meet here again at 11.